All right, welcome to class number 3. Maybe before we begin, just some administrative stuff. There's a grade scope instance for this class, and if you were registered as of 2 days ago, you should all have been invited to it. So hopefully you're all like a member of the grade scope account for this class. So that's how you're gonna turn in your problem set when it's due. We've started posting the office hours schedule on Slack. I had my inaugural office hours today. They were attended by the inaugural students. So, take advantage of those. And hopefully everyone's taken a look at the problem set and has started doing it so that you can take advantage of the office hours as they come up. So before we begin today's material, are there any questions about just the administration of the class? Okay. So if you remember last class, we sort of went over the basic definitions of game theory. What is a best response? What is a dominated strategy? What is a Nash equilibrium? And along the way, we saw some of these like standard sort of anecdotes of game theory 101, Prisoner's Dilemma, Boffer-Stravinsky, games like this, little games that you can draw as like a matrix, and you can like look at them and you can understand them. But in general, like in this class, first of all, little 2-player games are quite limited in what they can model, and there aren't, computation, which is one of the main things we're going to focus on in this class. It doesn't really become a problem for 2-player games, and anyways, there's sort of little interest in studying 2-player games. So in general, in this class, we're going to try to develop ways of thinking about large games, N-player games. And so we'll sort of give our first example of that today. So today we're going to go through sort of a complete case study of some large structured class of games. And there's all sorts of problems with large games. First, how do you even like express them? We're going to have to think about how to express them in a concise way, even to like think about them, and that's going to require structure. But we've talked about Nash equilibria. In a very large game, even if we believed it had pure strategy Nash equilibria, and remember, as we saw last time, not all games do. Now there's sort of the state space, the set of all possible permutations, choices that all of the players can make. And the state space is exponential, and so the existence of Nash equilibrium on its own doesn't really give us any guidance as to how to find it. And so it's not clear that Nash equilibria, even if we think that they are sort of a plausible conjecture for what a stable state should look like, would give us any confidence that we would get to one, we would get to a stable state. And so we're going to study in this class a simple natural dynamic, something that is hopefully computationally plausible, by which I mean doesn't require like vast resources, either computational or informational on the part of any of the agents, and is like a reasonable thing for them to do, and show that it converges to Nash equilibria. And that'll be something that hopefully gives us confidence, at least in the class of games we're going to talk about, that maybe pure strategy Nash equilibria are reasonable predictions for what might happen. So this will be our first sort of computationally plausible set of predictions in a large interaction, but this will be sort of a running theme in the class. Okay, so just to sort of start us off thinking about large games, suppose I have like a general N-player game. Each of the players has K actions. Even if I just want to like tell you the utility function for one of the players, how many numbers might I have to write down? Like how big is a large game? Like N players, K actions. How many numbers do I need to write down for you to tell you the utility function, even for just one player? Yeah. Exactly. Yeah, like what's a utility function? It just tells you, for a utility function for one player basically tells you, in particular, like like a preference ordering over all of the states in the game, how much this player would like the game to arrive at one of its particular states. And how many states are there in the game? Well, each player can choose one of k actions independently of one another, and there's n players, so there's k to the n of these. Right, so k to the n numbers just to tell you one player's utility function. And then I'd have to do this n times to tell you all of the players' utility functions. That would define the game. And this would just be like an unreasonable object. Like forget about thinking about people being, like optimally rational playing in this game well. Like you just, for large n, you just couldn't like look at this thing and have any idea what was going on. This is just going to be like an object that is too big to fit in your brain, too big to fit in the brain of anyone playing in this game. So like, unless we impose some additional structure on large games, it just seems crazy at the outset to think about playing in large games in any kind of optimal way. So, it doesn't mean we shouldn't think about large games. What that means is we shouldn't think about structureless large games. If we're going to think about large games, we have to constrain ourselves to thinking about games that, despite the fact that they have many players, despite the fact that perhaps each player has many actions, has some kind of concise structure that makes it easy to think about. Okay, so maybe like the first example of such a game and an instance of the class of games we're gonna talk about today are traffic routing games that we talked about sort of informally in the first lecture. And just to, we're gonna define all of this formally in a moment, but just to give you sort of an intuitive sense of how a traffic routing game might be defined, what we're gonna have is some underlying graph. Okay, so there's like vertices and edges. Okay, think about this as like a road network. Specifying how things are interconnected. And players will be identified, there will be n players. Okay, and think of each player as being identified as some starting location and some ending location on the graph, possibly different for different players, but maybe player 1 wakes up here at their starting location, their home, and would like to drive to here, their ending location, maybe their office. And similarly, all the other n players might have a starting location and an ending location, and the action space for the player might be the set of paths in the graph going from S to T, which note might be really big, right? Like the number of paths in the graph going from S to T could be exponential in the number of edges in the graph, in the number of edges in the graph, or the number of vertices in the graph, right? Because if I have a graph that looks like this, I have like an independent choice to make at every layer of the graph, and I can make each of them differently. So the strategy space can be really large, but it's easy for me to tell you what the strategy space is, right? I don't have to enumerate an exponentially large set of actions. I tell you the graph, and then I say, okay, it's the set of ST paths in the graph, a concise representation. Okay, and it's supposed to be a game, right? So it's supposed to matter to you what the other people do. And so, the way that is represented in like a traffic routing game is there's a congestion function on each edge, okay? Separately for each edge that tells you how congested a road is as a function of the number of people who are playing on it. Okay, so everyone will choose a path. This will in particular tell you how many players are driving on each road segment. You can plug it into this function to figure out what is the congestion on that road segment. And you sum up those congestions along your path to figure out what your total commute time is. Okay, so we'll define a more general class of games that captures all of this formally in a moment, but this is just sort of maybe to put a picture in your mind to think about how we might define a class of games that has a lot of structure that lets us write down something relatively simple that you can think about, right? If I want to think about how to drive in Philadelphia, I don't have to like imagine some like exponentially large object. Like it's enough to sort of have some idea of what the Philadelphia road network looks like and what traffic is on different routes. That lets us think about games that implicitly have large numbers of players and large numbers of actions. Okay. Questions? Yep. That's right. Which is important if we want this to be a concise representation, because there's potentially exponentially many paths in the number of edges. Okay. So let's now give a formal definition for the class of games we're going to talk about today that will include, in particular, things that you will recognize as traffic routing games, as well as some other stuff. And the way we define things last class and sort of the tradition in game theory is that players want to maximize their utility. But it's going to be more natural in congestion games to talk about players who want to minimize their cost. You want to minimize like your commute time from S to T. And mathematically, these things are equivalent. If I wanted to phrase it as maximizing utility, I could just say your utility function is the negative of your cost function. But to avoid having to do that all the time, I'm just going to, for this lecture and for some of the future ones, talk about players who want to minimize costs rather than maximize utility. But don't let that throw you off. It's the same thing. Okay, so what's a congestion game? Well, it's a game, so I have to tell you who are the n players within it. Okay, and now we start to get to some aspects in which these games are more structured than general games. So I'm going to introduce this set of objects called facilities. And in general, this can be just some abstract set of m things, but maybe to keep something concrete in your mind, if you're thinking about like a traffic routing game, think about the facilities as being the individual roads in the road network. So the set of facilities might be the set of edges in this graph. Okay. And each player is going to have a set of actions, but the set of actions will not be arbitrary. Each action will be identified with a subset of the facilities. Okay, so the action set will be a collection of subsets of the facilities. They can be arbitrary subsets of the facilities. Or rather, I can define a game whose actions are arbitrary subsets of the facilities, but each particular congestion game will assign an action set to each player that is some particular subset of the facilities. So for example, just to keep this all concrete and grounded, in a traffic routing game, if I am a player whose starting location is S and whose ending location is T, my action set would be the set of all ST paths, which are a particular collection of subsets of the edges, right? Paths are subsets of the edges. So in general, in a congestion game, the action set for each player will be a subset of the facilities, a collection of subsets of the facilities. Each action is a particular subset of the facilities. And for each of the facilities, we identify some cost function. Okay, for facility J, I'll write that as Lj. And this function maps an integer between 0 and n being the number of players in the game, to a real number. And you should think of that as sort of meaning, Lj of k is the cost of facility J when k players are using it. Okay, so this is sort of like if we're modeling a traffic network, this is like, what is the time to traverse this stretch of road as a function of the number of cars that are driving on it. Okay, like for a traffic routing game, you'd sort of expect that the cost would go up the more people were using the road. But the definition of a congestion game doesn't require that this cost function be monotone. It might be interesting sometimes to think of games where the cost goes down when more people use it. Okay. And in particular, the cost of a facility does not depend on who is using it, just the number of people who are using it. Okay, so this is another sort of important structural property of the game. Like to describe one of these things, to describe a cost function that sort of cared about the identity of who was using it would require, again, an exponential in n number of numbers. There's a lot of subsets of the users, but if we only care about the cardinality of the set of users on the facility, then this is sort of a concisely defined function. Okay, and so finally, what are the utility functions for the players? Or since we're going to be talking about costs, what are the cost functions for the players? So remember, what we need to specify is what is the cost for each player as a function of the choice of action for themselves as well as for all of the other players, as a function of the choice of action of all of the players. Okay, so each player chooses an action, which is a subset of the facilities. And given such a play profile, I can now ask the question, well, on each of the facilities, given what everyone is doing, how many people are using that facility? How many people have played an action that contains as an element that facility J? Okay, so I'll just write as shorthand nj of A to mean at action profile A, how many people are playing on facility J? And then the cost of an agent in this game, the cost of a player in this game, given a play profile, given a choice of action for each of the players, is just the sum over all of the facilities that that player is using. Remember, an action is just a subset of the facilities. Okay, so summed over all of the facilities that that player is using, the cost of that facility, given the number of people that are on it. Okay, so again, just to keep things grounded in traffic routing games, everyone chooses an action in a play profile. That means everyone decides a route they're going to drive from home to work. Everyone picks a path in the graph. That tells us sort of the level of congestion on each of the roads, the number of people using each road segment, and the time it takes to traverse each road segment, given the cost function for that road segment. And then your total commute time, your total cost, is the sum over all of the road segments that you personally have decided to drive on of the congestion on that road segment. Okay, so it's a pretty natural class of games, a pretty good model, I think, for traffic routing games, but this is just like a slightly more general class of games that captures that. Okay, so why don't I pause here? This is the class of games we're going to study today. Why don't I pause here to let you digest this and take questions, because I want to make sure, there's some abstraction here, but I want to make sure that all of this makes sense as a definition, and in particular, it's clear how these things map onto maybe the more intuitive idea of a traffic routing game. Are there questions about the notation or the definition or the objects we're talking about here? Yeah. That's right. Yeah. So the cost function depends on the facility. There's a different cost function for each facility and on the number of players using the facility, but it doesn't depend on anything else. So in particular, given that you and I are both traversing this road segment and there's 1,000 people trying to do it at the same time, it takes me the same amount of time to do it as it does you. It's not that like you've got an airplane or something and can go over the traffic. Yes.
So would be the specific player, right? So then, are we also adding up the cost of these other players are using?
So the cost, so your cost as an individual player depends only on the facilities you are using. The facilities other players are using contribute to their cost, but not to yours. So for example, if I'm driving from home to work along this central path, and there's a huge amount of congestion on some road I'm not taking, that doesn't slow me down.
Yeah. Like taking into account if like other players have used the road previously too. Like if
so there's no notion of time here. Yeah, so like, right, it's true that like in real life time exists, but in this model there's no notion of time. Like this is sort of a static, everyone chooses a path and you contribute to the congestion to every road in the path simultaneously. Good question. Others? Okay. Maybe just to sort of briefly talk about a very closely related set of games to traffic routing games, but that have a bit of a different flavor. In traffic routing games, maybe the motivating story is like this road network, it already exists, it's been built. And what we're measuring is the amount of time it takes for you to drive down each of the roads. And so the more people that are on the road, it takes more time. So, these cost functions per facility, they're increasing. More people on the road, like more congestion. But note that we do not require in the definition of a congestion game that these cost functions be increasing functions. So we could also consider what are called network creation games, where again you'd have a graph, but maybe now the model would be, these are places where we could build road or we could build fiber optic cable or whatever. And there's different players who would like to connect different endpoints in this graph. And to actually connect them, you'd have to actually build these roads or stretches of fiber optic cable or whatever, and that would come at some cost. But that if you and I both want, have different points we want to connect, but there are paths that involve the same segment, then maybe we can share them. And we can split the cost of building them. We can sort of team up and split the cost. So maybe there's some cost of constructing an edge, say $C. And if I'm the only one who's going to use the edge, if I want to build it, I have to pay $C. But if you and I are both going to use it, then each of us only has to pay C over $2. And if there's 3 of us who are going to use it, each of us only has to pay C over $3, meaning, there's a fixed cost of construction for each facility, but we can share the cost across people who are going to use it. Okay, that kind of thing is also a congestion game. Okay. We'll think about games like this a little later in the class, but this is just to point out that, that congestion games have a very particular structure, but there's a little more flexibility here than just modeling like traffic routing, for example. Okay, so we've got some class of games, and at least I can tell you what the game is, and with sort of a relatively small amount of information. I can sort of describe the game to you without these sort of k to the n numbers, and so there's some hope at least that people could maybe figure out how to think about such games. Okay, so it's so what? What can we learn about games in this class? Can we make use of this structure to say anything interesting? So questions we could ask, right? Do games in this class have pure strategy Nash equilibria? If we're going to try to make predictions for what might happen when people play in games in this class, what should our predictions look like? We know that every finite game has a mixed strategy Nash equilibria, but I don't know, are people really going to randomize? Like, are you going to flip coins when you're deciding where to go to, what route to drive on in the morning? It would be nicer if we could, if we could talk about pure strategy Nash equilibria, but of course, like we can't if they don't exist. So the first question might be, do games in this class have pure strategy Nash equilibria? Even if the answer were yes, right, these are still like very large games. Why should we think that computationally bounded agents who are not coordinating with one another might have only sort of a limited view of the state of the game? Like maybe they can get traffic reports, but they don't know, specifically who's doing what. Is there any reason to think that these sort of simple, uncoordinated players could find one? Even if the answer to the first question is yes, they have pure strategy Nash equilibria, but the answer to the second question is no, then it's not clear that they're going to be good predictions. Okay, so like these sub-questions are just adding up to the overall question: are pure strategy Nash equilibria computationally plausible predictions in this class of games? So that's the question I want to try to answer today. And so, right, the question is, can computationally bounded, uncoordinated players find one? Well, what are they going to do? Like, why don't we start by thinking about a particular simple thing that they might do, and go from there. So I want to talk about something that I'll call better response dynamic, and I'll describe it to you in pseudocode in a moment, but it's a super simple idea. So let me just tell you what it is first. Oh, and although I'm going to write this out in pseudocode, there's going to be a lot of things that are left unspecified, like in this first line. What is the starting point? Well, it can be arbitrary. And that's going to be a strength in that whenever there's something unspecified, like what's the starting point of the dynamic, the answer will be it can be anything. And the things we're going to prove about it will still hold. Okay, so if we want to sort of think about this as not an algorithm that you're going to run on a computer to compute Nash equilibria, which you could, of course, think about it that way. But if we're not going to think about it that way, but as instead a model, still at a 10,000-foot view, but a model for what people might actually do, then the less stringent our model is, the less we assume specifically what they're going to do and allow them to do anything in some class of behaviors, the more plausible our model will be. Okay, so some dynamic, it'll have some starting point, but I don't care what the starting point is. It could be anything. Okay, so everyone starts off playing arbitrarily in this game. They pick some route. It doesn't have to be a good one or a bad one. And then you sort of imagine that, okay, every day the sun comes up, you have to drive to work again. You play this game again. And sometimes, maybe like you don't have fine-grained information about what people are doing, but maybe the kind of information you have is the kind of thing you can get from Google Maps or like a traffic report. Like you have some idea for what the congestion is on each of the roads, or at least what it was yesterday. Okay, so you might notice that you were doing something that was suboptimal, that was not a best response to what everyone else was doing. There's something else you could do, you could change your action to, that would improve your utility, that would sort of decrease your commute time. And so in arbitrary order, players will take turns changing their action if there's an action that they can switch to that will improve their utility. Okay, and just sort of emphasizing the things that are underspecified here. Okay, I'm thinking about a sequential dynamic where people are changing their strategy in order, but it doesn't matter what that order is. And I'm not assuming necessarily that they're changing their strategy to their exact best response, that they're playing the thing that exactly minimizes their cost. I'm just assuming that they're changing their action to something that decreases their cost. There could be many such things, and I don't care which one they pick. Yeah. Yeah, I mean, it could be. Like a greedy approach would sort of be, pick the absolute best thing you can do given what everyone's doing now. I'm not even requiring they do the absolute best thing, just something that improves a little bit. And this will just keep going forever or until it can't go anymore because everyone's doing the best that they can be already. Okay, so this is sort of the high level idea of what best response dynamics is. And so just to write it down in a way that's harder to understand, here it is in pseudocode. But it's exactly what we said, right? Like you start at some arbitrary action profile. While there exists a player whose current action in this action profile is not a best response, by which I mean their action is not one that minimizes their cost given what everyone else is doing, then we let them change their action to something that does better. We can let them change their action to AI prime, where AI prime can be any action that has lower cost given what everyone else is doing compared to what they were doing before. Doesn't have to be the one that optimizes it, just lowers it. Then they change their action and we continue. And if we, only if everyone is playing a best response do we break out of this loop. This is what I mean by better response dynamics. Is it clear? So you can think about this as an algorithm, if you like, with certain things that can be, certain things that are underspecified and can be instantiated in arbitrary ways, or you can think about it as some model for what people might do. But is it clear what is this like dynamic that we are now going to try to make claims about? Okay. So let's start simple. So like, this whole dynamic, it's a big while loop. It's not clear this thing is ever going to halt. Right? It might go forever. Maybe it doesn't converge to anything. Maybe people, maybe like right? It could be that repeatedly I change my action to something that decreases my cost, but it increases your cost, and then you change your action to something that decreases your cost, and it increases my cost, and we go back and forth forever. So a priori, it's not at all clear that this thing is going to halt. But I claim one thing that is clear is that if it halts at a pure strategy Nash equilibrium of the game. And can anyone tell me like the one-liner explaining why this is? Yep. Yeah, it's like it is the halting condition of the algorithm, right? Like, what is the halting condition of the algorithm? It is that everyone is playing a best response to what everyone else is doing. If that were not the case, if there was someone who was not playing the best response, we would not have halted. So like just by reading off the halting condition of the algorithm, it must be that if the while loop if we ever exit the while loop, if this dynamic ever halts, the thing we return is a pure strategy Nash equilibrium, which just means it is an action profile so that simultaneously every single player is best responding to what everyone else is doing. That is the halting condition of the algorithm. Is that clear? Okay, so if we want to show that best response dynamics converges to a Nash equilibrium, which in particular will prove there exists pure strategy Nash equilibria, it's sufficient to argue that this algorithm halts. If it halts, it halts at a Nash equilibrium. Okay, so the next question is, the next question is, does best response dynamics always halt? What do we think? Like, might it be that in every game, best response dynamics halts? Is that a theorem we could hope to prove? Yeah, let's play rock, paper, scissors. Rock, scissors. Ah, got me. So, okay, right, like best response dynamics does not always halt, right? We can do rock, paper, scissors, and it's going to cycle, right? And the problem is what's happening is exactly what I said a moment ago, that it might be that every time you best respond, you decrease your cost and increase my cost. And the reverse happens when I best respond. And that's what's happening in rock, paper, scissors. My cost going up, then down, then up, then down. We're just cycling forever. Okay, so best response dynamics, like if our hope was to prove best response dynamics always halts, like we're out of luck. It's just not true. I mean, in particular, like if it halts, it implies the existence of a pure strategy Nash equilibria. So it can't possibly halt in any game that doesn't have pure strategy Nash equilibria, like rock, paper, scissors. Okay, but what I want to prove is that although best response dynamics does not always halt in general, in congestion games, best response dynamics does always halt. And in particular, a corollary of this, right? Like this is going to be a statement about an algorithm, right? Like we wrote down an algorithm, and the theorem is the algorithm halts. But like a corollary of this statement about this fact about that's going to come out of the analysis of algorithms is just like a structural theorem about this class of games, right? It means in particular, it must be, if best response dynamics always halts in congestion games, that every congestion game has at least one pure strategy Nash equilibria, right? Like this is not an obvious structural theorem. Like not all games have pure strategy Nash equilibria. But if we can prove this fact about best response dynamics that it halts, that will in particular prove the existence of pure strategy Nash equilibria for every game in this class. Okay, is that implication clear? And just to sort of like highlight this kind of implication, because it's going to be a running theme in this class, right? This will happen more than once, that we sort of get some non-obvious structural theorem about a class of games through the analysis of some particular algorithm. Okay, so this is like the first instance of that. Okay. So let's think about how you might prove something like this. Right. So what is the concern? Right. The concern is that we get into a cycle. Like these are finite games. They're big, but they're finite. So if this never halts, it means that if we keep playing this game via best response dynamics, eventually we're going to get back to exactly the same game state that we started at. Okay, or maybe not the one we started at. We're going to visit the same game state twice. So that like the kind of thing we need to prove is that we can never visit the same game state twice, that we are making progress according to some metric. The metric might not be obvious a priori, but if we can identify any metric along which iterations of best response dynamics are making progress, then an implication will be that we can't loop back to a state we've previously visited. So that's going to be the idea. We want to identify some potential function, some function mapping game states to like real numbers. And we want to argue that that potential function can only go in one direction, can only go down as iterations of best response dynamics progress. And an implication of that is that we can't get back to the same game state twice, because a potential function maps game states to potentials, to numbers. And if the number is only going down, if we get back to the same game state, it must have at some point gone back up. And if we prove it can only go down, that can't happen. Okay, so that's the high-level proof strategy. Now, of course, the question is, what is the potential function? This is the potential function we are going to use. So I'm going to read it out to you, but let me state off the bat that like, this is not an obvious quantity of interest a priori. This is going to be useful for us because of the role it's going to play in the proof. Okay, so like when you first look at something like this, you might think to yourself, okay, this maybe kind of looks like social welfare, the sum of the costs of all of the players, right? That would be a natural thing to think about. Like, what is the average commute time of all of the players? And it would be nice if every step of best response dynamics decreased the average commute time. And then average commute time would be a potential, and also like this would be an interesting statement in its own right. Unfortunately, that's not true. And this is not social welfare. This is not the sum of the costs of all of the players. So what is this function? Well, first we're summing over, so first of all, it is a function of the sort that I promised. It just labels every game state with a number. It's a map from game states to real numbers. And what number does it label a game state A with? Well, first we sum up over all of the facilities. And then for each of the facilities, we look and we say, okay, at this game state, how many people are playing on this facility, nj of A? And then we sum from 1 to the number of people playing on that facility. Right, so k is 1, then k is 2, all the way up to the number of people playing on the facility. And what we're summing up is the cost of that facility when there are k people on it. Okay. Not obvious why you would care about this, but it's the reason is going to pop out of the proof, and you can imagine how to, given the thing that we're going to prove, how if you knew that was what you wanted to prove, you could sort of reverse engineer what you needed to get this potential function. Okay, so remember the outline, the proposed proof outline. I'm going to argue. It's not meant for t-shirts. Oh. We want to argue that at every round of best response dynamics, this function decreases. So the thing we need to think about is how this function changes when some particular player, say I, switches from action AI to BI during some step of better response dynamics. Okay, that's like the thing we need to think about. If we can show that the change is strictly negative, then we'll be done. So let's start by thinking about something a little bit different, but whose relevance will become clear shortly. Rather than thinking about the change in potential when player I changes their action, let's think about the change in player I's cost. Because that's something at least we can hope to get some handle on, because we don't know much about the individual changes that make up the rounds of better response dynamics. Mostly it's underspecified. But the one thing we know is that these changes, by definition, must decrease the cost of the player who's making them. That's why they are making them. They're better responses. So we know that the change in player I's cost, the difference in player I's cost after they make their switch from AI to BI compared to before they make their switch, that difference is going to be negative, because that's the one thing we know about better response dynamics. Players decrease their cost. And so what is that change in cost going to be? Well, remember what a cost function looks like for a player in a congestion game. It's the sum over all of the facilities that they play on of the cost of that facility given the number of players that are also playing on it. And so suppose I switch from playing a subset of the facilities AI, like a path and a graph AI, to a different subset of the facilities BI, like a different path in the graph. Well, it might be that these paths are not completely disjoint. They might intersect a little bit. Like if I live in the suburbs on some cul-de-sac, I might have choices for how to get into Penn, but there's no avoiding that first I'm gonna have to drive down my driveway and drive down the road, and the beginning and end of my path might look the same, right? So these AI and BI are not necessarily disjoint. So first of all, if I look at any facility that I play on, both in my new action BI and in my old action AI, it contributes exactly the same amount to my cost, both before and after my switch. Right? because nothing's changed. I still play on that facility. I still drive down that road segment. And this, it's only me that's changed my action, and I didn't change my action relative to this road. So the number of people playing on the road hasn't changed. So facilities that I play on both before and after the switch, they contribute the same amount to my cost before and after the switch. And so they cancel out. They don't appear in the difference in costs. Similarly, facilities that I don't play on either in BI or AI don't contribute to my cost in either case, and so don't contribute to the difference in cost. Right? The only facilities that contribute to the change in my cost when I switch from a subset of the facilities BI to a subset of the facilities AI are those facilities that are in the symmetric difference, are those facilities that either I previously was not playing on but now am, or the facilities that I previously was playing on and now I'm not. Okay, so there's some facilities that are in BI, my new set of facilities and my new action, that I previously was not playing on, but now am. Okay, I wasn't paying for the cost of those facilities before, and now I am. So they're going to contribute positively to my change in cost. So I'm going to have to pay the cost of those facilities, and the cost of those facilities is not just the number of people who were playing on them before. It's that plus one, because now I'm there, right? I've increased the load on those facilities by 1, so that my cost has gone up on the one hand by the cost of all of the facilities that I've moved on to, where the number of people playing on those facilities is now 1 more than it was before. But on the other hand, it's gone down by the cost of all of the facilities that I was previously playing on and experiencing the congestion of that I no longer am. Okay, so I can write my change in cost if I, in one round of better response dynamics, have switched my action from AI to BI like this. The sum over all of the facilities I moved on to, taking into account that there's now 1 more person on them, minus the sum of all of the facilities that I moved off of at their load yesterday. Yes. Because this is what I was paying before I changed my action. So it's true that after I move off of this, everyone else on these facilities gets to experience the joy of not having to be around me, and their cost has decreased on those facilities to LJ of NJ of S minus 1. But yesterday, before I moved off, I was paying the cost of the facility, including my own presence there. Does that make sense? Typo, should be A. Yeah. Yeah, so NJ of A, this is the number of people who were playing on facility J at action profile A, which is the action profile that we were at before I changed my action. Now, these are facilities that I wasn't playing on in action profile A, but that I am now playing on in this new action profile that I get by changing my own action, but not everyone else's. And so now there's 1 more person playing on these facilities. That 1 more person is me. So, yes, exactly. These are not all of the facilities I'm playing on. These are exactly the facilities that I'm playing on now that I wasn't playing on before. And of course, the ones that I was playing on both now and before, they just canceled out in this difference. Does that make sense? Good question. Other questions? Okay, so this is an expression for my change in cost. And I don't know much about better response dynamics, but like the one thing I know is that whatever this is, it's negative, because that's the definition of better response dynamics. But a lot is left unspecified, but when someone changes their action, they do so exactly because it decreases their cost. Okay. So now let's think about what is the change in potential when a particular player changes their action from AI to BI. Okay, and we can go through sort of much the same exercise. So let's think about the potential function again. It is a sum over facilities. Okay, and on each facility, we're summing from k equals 1 to the number of players on that facility. So if we look at the potential before, the potential after my change, minus the potential before my change, I can think of this difference facility by facility. And there will be some facilities such that the number of people playing on them has not changed. In particular, those facilities that either I was playing on both before and after my change, or the ones that I wasn't playing on before and after my change. For those facilities, the number of people playing on them won't have been affected by my change in action, and so their component of the sum is just going to be like the same before and after, and so they're going to cancel out in this difference. The only facilities whose contribution to the potential is going to change are those facilities such that the number of players playing on them has changed. Okay? So again, there's two kinds of facilities like that. There's facilities that I was not playing on in A, but I am playing on in B. What's the change in potential going to look like as a contribution from that facility? Well, previously for that facility, we were summing from k equals 1 to nj of A, the number of players on that facility. After the change, well, nj of A increased by 1. So we're now summing from k equals 1 to nj of A plus 1. And so we have the whole sum that we had before plus one additional term. What's that one additional term? It's nj of A plus 1. Okay, and so the additional contribution to the potential from the facilities that player I switched onto, well, it's going to be the load on the facility when nj of A plus 1 people are on it, because that's the extra term that's added to this sum when we increment the number of people playing on the facility by 1. And then there's another kind of facility that has had the number of people playing on it change. It's the facilities that player I moved off of when he changed his action. Okay, now previously, when he was playing action AI, there were nj of A people on that facility. Now that he's switched his action to something that does not contain facility J, the number of people playing on that facility has decreased to nj of A minus 1. Okay, so the contribution of that facility to the potential is now a sum not from k equals 1 to nj of A, but a sum from k equals 1 to nj of A minus 1. And when we look at the difference in those two sums, what is the term that has been removed in that difference? Well, it was the biggest term in the sum. It was nj of A. And so what we subtract off when we look at the change in potential on those facilities that player I has moved off of, those facilities that he had been playing in action A, but is no longer playing in action B, well, the sum, which corresponds to the contribution of that facility to the potential, is no longer contributing this term, which is the loss of the facility when nj of A people are playing on it. Okay? Does that make sense? Yes. So we have not specified particular congestion games. The claim we are making now is for the set of all congestion games. This is the potential function that we are using for this proof, which is applying to all congestion games. Now, at various times, we will try to adapt this analysis to other classes of games. I think on the next problem set, you are asked to do so, and you will need a different potential function. And part of the We'll see several variants of this style of proof. Like it's basically all mechanistic once you have the potential function. You have to think like, what is the change in potential when someone changes their action? Most of the cleverness is in coming up with the potential function. And although there's not exactly a crank to turn to do that, like one thing that you can often try to do is what we've done here is to try to rig things up so that the change in potential is exactly the change in playerized cost. That's sort of how this potential function is designed. Exactly. You want the potential. You want to be able to argue that the potential function decreases at every round.
What does the potential function represent?
The potential function does not necessarily represent any natural quantity in the game. It is a tool in the proof to argue that you cannot get into a cycle.
Does it not represent like the total time spent across like all players?
It does, yeah, no, that would be the social welfare or the social cost. And if you write down what is the sum of the costs of all of the players, you'll get something that is not this.
That's such that after each of the cost, such that when there's that new n plus one or L of n plus one, there's a new kind of sum being added to the new term.
Exactly. Exactly. Like you can figure out what is the change in cost to a player, and it's this. This is, this is what it is. And then if you were now trying to design a potential function to make this proof work out, what you'd want to do is design the potential function exactly so that this would be true, so that the change in potential would be equal to the change in cost. So you know what the change in potential has to look like. So it's sort of like a discrete derivative. You want to take the discrete integral of it or something. Okay. By the way, we're not quite done with the proof yet. But these are all good questions. Right, so is this clear? Is it clear where we are at the moment? That we've sort of argued that the change in potential when a single player changes their action from AI to BI, it's exactly equal to the change in cost for that player. And we knew that if this is true in general, this statement has nothing to do with better response dynamics, right? Like this was just like an algebraic identity. The change in potential is equal to the change in cost of the player. But if this was a step of better response dynamics, the change in cost had to be negative, right? Players were, by definition, the only thing we assumed about this dynamics was that the changes were such that they decreased players' costs. And so if this was a step of better response dynamics, this change actually has to be negative. And so in particular, if we imagine tracking this potential function as better response dynamics goes on, it starts at some value. Every step of better response dynamics strictly decreases it. And this can't go on forever because it's a finite game. Right? In particular, we can never visit the same state twice, because that would imply that at some step, the potential would have had to go up, which we showed can't happen. Okay, and so best response dynamics halts in congestion games, and in particular, halts at a pure strategy Nash equilibria. And in particular, this proves the existence of pure strategy Nash equilibria in congestion games. Is that clear? Like it's kind of neat, right? Like we just sort of thought about this algorithm, and we proved that in this class of games, pure strategy Nash equilibria exist. We didn't know that before. And we even have a story for how you might find them. It's sort of the inevitable result of people sequentially changing their actions in sort of self-interested ways to decrease their own cost. Like it's not just like pure strategy Nash equilibria in this class of games are no longer just a stable point, but they are sort of an attracting point of this class of dynamics where people are going to sequentially try to decrease their own cost. Like this class of dynamics will inevitably get you to a pure strategy Nash equilibria eventually. And so maybe it's a reasonable class of predictions. Yeah. The image of phi is real numbers. Well, it depends what you mean by the image. The range of phi is real numbers, but it doesn't map onto all of them because although there's a lot of game states, there's only finitely many.
So why is that the potential if it just ends up with the cost? Like, why don't we just use the cost directly?
Whose cost? Well, there's n different players. So when I make a better response move, my cost decreases. But when you make a better response move, my cost likely increases. Right, like if that could happen very easily. You move onto a road that I'm taking now, it takes me longer to drive to work. So when you make a better response move, your cost decreases. When I make a better response move, my cost decreases, but your cost goes up. If we were just paying attention to individual player costs, that wouldn't rule out the kind of cycling we're worried about. We need a single consistent measure that goes down at every time to rule out cycles.
So what exactly is delta CI first?
So here, I mean, we hadn't yet proven anything about the game, but we identified that when player I changes their action, their change in cost is equal to this algebraic expression and it's negative, which allowed us to realize, right, but this was the change in cost for a particular player. There's n players, and this thing might go up again when you take your turn. But now we're looking at this single potential function. And we're saying, when player I changes their action, whoever player I happens to be, when any player changes their action, the change in potential is equal to the change in player I's cost. And this thing is negative if player I was the one who changed their action. So now we have this single number that is decreasing at every round when different players change their actions. And this is what we need to argue that we don't get ourselves in cycles. Make sense? Yeah.
What's the significance of the converse operator?
The significance of what? Oh, I just mean, this is how I'm defining it. This is like a definition. Good question. Other questions? Yeah.
Like so far, it seems like everything is like super general. Like, but what is like a property of congestion?
A couple of things. So we're using crucially that congestion games have this notion of like facilities, first of all, like most games don't. Like the potential function is defined over these facilities. We're using crucially that the cost of a player is the sum of the costs of the facilities. That was how we derived this expression for the change in cost. And we're using crucially that the cost function at each facility depends only on the number of players playing on it and not on anything else. So we're sort of using all of the structure. But not more than that. So this result holds for any game that can be described as a congestion game, of which there are quite a few. Okay. Yeah.
The way that it's defined is almost like you're starting with like an empty game state, and then you're imagining like the first person arrives at each feature.
It doesn't have to be an empty game state. You can start at an arbitrary game state.
Yeah, sorry. I guess that's like more like the never mind. I think I'll think about this later. But like the second term, like the second summing term seems like it's like if you remove the sum and replace it with the nj of a, you would have a social welfare function, right? Or like,
You might have to, it might be like nj of a, it might be like nj of a times lj of nj of a. Like you'd have,
I see.
Yeah.
Just to clarify, so for any game we define as a congestion game, we have agents, vicinities, and just that the sum of the boss of the agent is the sum of the boss of the vicinity.
Yep.
So those agents,
and that the cost of a facility is a function of the number of agents on it.
and if those four things, you can transform anything to that
then we have proven that best response dynamics converges. Good questions. Other questions? Okay. So we sort of said, okay, better response dynamics is great. Like, start any state you want, let the players move in any order they want, let them take any better response that they want, no matter what, they will inevitably lead themselves towards a pure strategy Nash equilibrium, and therefore pure strategy Nash equilibrium might exist. Something we have not addressed here is how long it takes. Like, strictly speaking, all we have proven is that the dynamics never visit the same state twice. But, like if there's n players and k actions, there's k to the n states. And in a congestion game, like k could be exponential itself in the size of the graph. So, like, it doesn't mean it's going to be fast. And like, although I'm not going to give the example, like, indeed, you can draw graphs and give orderings of players that conform to how we defined better response dynamics that really do take exponential time to converge to a Nash equilibrium. So, is there any hope? Like, can we say anything non-trivial about convergence speed? And the answer is yes, if we're willing to think about approximation. So what do I mean by that? So the way we've defined a pure strategy Nash equilibrium so far is we've said, look, everyone should be playing simultaneously an exact best response to everyone else. Nobody should be able to improve their commute time by even a microsecond. But we could define a slightly relaxed version of that. We could say, look, a strategy profile is going to be an epsilon approximate pure strategy Nash equilibrium. If everyone's playing an approximate best response, if there's nobody who could reduce their commute time by more than a second by changing to a different route, or half a second, or a tenth of a second, or whatever, some finite epsilon bounded away from 0. And the thought might be that if there's any friction to changing your action, if it's like a little annoying to do so, then maybe like below some threshold of gain, you're not going to bother doing it, and it's going to be stable anyway. Like, I don't know if you've been driving with Google Maps and never get these alerts that say, you get off like 95 here and take this crazy route, and it'll save like a minute, and have decided not to do it. I generally decide not to do it because of the cognitive load, despite like leaving that minute on the table. And if you believe that people sort of might think like that, then you might think that approximate pure strategy Nash equilibria, at least for small enough epsilon, are at least kind of stable. And so let's take that seriously and think about a version of better response dynamics where it's exactly the same as before, except now we're going to imagine that there's some threshold epsilon so that you're not going to bother changing your action if it won't decrease your cost by at least epsilon. Okay, so if there, we'll keep going forever while there is a player who's not playing an epsilon best response, who can't decrease their cost by at least epsilon. And as long as there is one in arbitrary order, we'll let them change their action to decrease their cost by at least epsilon. But if we end up at an epsilon approximate Nash equilibrium, we'll say the dynamic is done. There's nobody who can improve their situation by decreasing their cost by more than epsilon. We'll declare the dynamic to have halted. And we can analyze this just as we analyzed the exact version of better response dynamics. And an immediate parallel is that we can note that, like, by definition, of the halting condition, if this dynamics halts, well, it halts at an epsilon approximate equilibrium. That was the halting condition. It halts exactly when there's nobody who can decrease their cost by more than epsilon, which is what an epsilon approximate pure strategy Nash equilibrium is. But now, in addition to proving that this dynamics halts, we can attach to it a rate. We can say that it actually halts pretty quickly in sort of time that is, individually linear in all of the parameters of the game. The number of players and the number of facilities and 1 over epsilon, the approximation parameter that we're thinking about. And C max, which is just an upper bound on like the maximum cost of any facility, like how long it takes you to traverse, the Schuylkill River Parkway, in the worst traffic you can imagine, which it's not nothing, but it's a finite game. It's only going to be something finite. Okay, so the claim is that in any congestion game, best response dynamics will halt at an epsilon approximate Nash equilibrium after only n times m times C max over epsilon many steps. And the proof is almost exactly the same as our analysis of the exact version. We use exactly the same potential function. We recall, just as before, that at any step of better response dynamics, the change in cost of any of the player who made their move is exactly equal to the change in potential. All of that's still true. But now we observe that our potential function, which we take a look at, first of all, is always non-negative. Because these facility functions, these individual facility cost functions, these are non-negative. And the potential is just a sum over a bunch of non-negative things, so it's non-negative. So at any moment in time, the potential at any game state evaluates to something greater than 0. And then the question is, it's going down at every step, but how large was the potential when it started? Well, we assume nothing about where it started, but we can still give sort of a crude worst case upper bound on how big this potential function could possibly be. We're summing up over all of the facilities, m, there's m of them, so let's pay a factor of m. We're summing up for each facility over the number of players playing on that facility in the game state. Well, in the worst case, that's all of the players. Can't be more than all of the players. Okay, so maybe each of these sums will actually sum over n people. Let's pay a factor of n here. And we're paying, each term in this sum is the cost of the facility when some number of people are playing on it. Well, each of those costs can be at most the maximum cost for that facility, which is just this number that we called C max. Okay, so super crude upper bound, but it's just saying, look, no matter where we started, the value of the potential at that action profile, it can't possibly have been larger than m times C max. And it can't ever get below 0. But at every round, the change in potential is equal to the change in cost. And we've assumed that people aren't going to bother to change their action unless they can decrease their cost by at least epsilon. So the change in cost, right, we start at this number. At every round, we decrease the number by at least epsilon, and we can't get below 0. So how long can this go on for? Well, if it goes on for more than n times m times C max over epsilon many rounds, we'd have a contradiction. We'd have gotten to something below 0. And so the theorem follows. It can't go on for more than m times C max over epsilon many rounds. Yeah. Because We said it did, right? Because this dynamic is modeling. Otherwise, it would have halted. Exactly. Like we're sort of imagining here that people are only changing their action if doing so decreases their cost by at least epsilon. Yeah. So like this is the difference. This is exactly the difference between this dynamic and the exact better response dynamics, and we're taking full advantage of that difference. Okay, so if we only want approximate Nash equilibria, we actually get good rates as well, right? So it's you know, at least for approximate equilibria, you know, maybe a fully computationally plausible story, a permissive, fast dynamic that doesn't require that anyone know anything heroic or have heroic amounts of computation, that inevitably leads us to pure strategy Nash equilibria. So thank you guys very much. I'll see you next week. Yeah, I can. This one. Yeah, I mean, epsilon can be whatever you want, but of course, the convergence rate depends by this theorem on 1 over epsilon. So if epsilon's 1 over 100, it's a factor of 100 here. All right, thank you guys.